Chapter 4, Exponential and Logarithmic Functions. Section 4.3, 3 Rules of Logarithms. When working with logarithmic functions, logarithmic expressions, we can often rewrite those expressions by knowing some basic properties of logarithms that are related to the properties of exponents that we're familiar with. So the 3 rules below allow us to expand or condense certain logarithmic expressions. The first of these rules is called the product rule and says that the log base a of m times n is equal to the log base a of m plus the log base a of n. That is, the logarithm of a product can be written as a sum of logarithms. The quotient rule says that the log base a of m over n is equal to the log base a of m minus the log base a of n. That is, the logarithm of a quotient is the difference of logarithms, or can be rewritten as the difference of 2 logarithms. And then the third rule, the power rule, says that log base a of m to the r is r times log base a of m. That is, we can move the exponent. If we have the logarithm of something to an exponent, we can move the exponent to the front of the logarithm and treat it as a multiplication. Now, for natural logarithms, the same 3 properties apply, but the notation is slightly different because for natural logarithms, which are base e logarithms, we use the ln notation rather than the log base a notation. So for natural logs, the product rule looks like ln of m times n equals ln of m plus ln of n. The quotient rule, ln of m over n equals ln of m minus ln of n. And the power rule, ln of m to the r is r times ln of m. So other than a slightly different notation, we see that the properties are exactly the same as what we saw above. Now, the rules of logarithms are directly related to properties of exponents that you're already familiar with. Remembering, of course, that a logarithm is an exponent. So logarithmic properties are directly related to exponential properties. The first property of exponents is that if you have a to the m times a to the n, where the base is the same in both cases, then we can add the exponents. So when you multiply and the base is the same, you add the exponents. It becomes a to the m plus n. If you're dividing a to the m by a to the n, you subtract the exponents. It becomes a to the m minus n. And then if you raise a to the m to the nth power, that becomes a to the product of m times n, of m and n, I should say. The first of these 3 properties of exponents corresponds directly to the product rule for logarithms, the second to the quotient rule, and the third to the power rule. Notice how with the first property of exponents, we associate a product with a sum. And that's exactly what we see with the product rule for logarithms. As you can see above, for natural logarithms, the natural log of a product becomes a sum of natural logarithms. For the second property of exponents, we associate a quotient to a difference. That's exactly what we see in the case of the quotient rule for logarithms. We associate a quotient to a difference. And in the third property of exponents, we associate raising a power to multiplication. That's exactly what we see here with the power rule for natural logarithms. Natural log of something to a power becomes a product. the exponent times the logarithm of m. So we could look at this in more detail and actually derive the properties of logarithms from the corresponding properties of exponents by converting the exponential forms into logarithmic forms. I'm sorry, excuse me, I have that backwards. We could convert logarithmic forms to exponential forms and then use properties of exponents to establish the corresponding properties of logarithms. And in fact, in the textbook, you'll see that that is, they show those derivations. I'm not going to do that, rather just indicate the relationship between the rules for logarithms and the properties of exponents that you're already familiar with. Now, in working with logarithmic expressions, we have to be aware of what we are allowed to do, that is, the properties that exist, but we also have to be aware of what we're not allowed to do. And there are a couple of things I want to draw your attention to that you have to be careful of that seem like they might be legitimate properties of logarithms, but that in fact are not things that we're allowed to do with logarithms. First of all, there are no general rules that allow one to expand log base a of m plus or minus n, that is, the logarithm of a sum or difference. In particular, we cannot split it up as log of m plus or minus log of n. It's a very common error. It's just an assumption students make. It looks as if it should be something you can do. It looks like you're applying some sort of distributive property, but in fact it's an invalid use of logarithms. Another common error that's made is to write the logarithm, a difference of logarithms, log of m minus log of n, as a quotient of two logarithms. Now, the quotient rule for logarithms would actually have us write a difference as a single logarithm of a quotient, not as a quotient of two logarithms, but as the logarithm, the single logarithm of a quotient. So log of m minus log of n is actually going to give us the expression that I just wrote there to the right, and not a quotient of two logarithms. So again, you want to write that as a single logarithm, not as two logarithms. Now let's look at some examples just to get a little bit more familiar with what we can do with logarithmic expressions. Example 1 says, express the common logarithm in terms of log of 3 and log of 5. We're not going to try to evaluate or approximate anything. We're just going to try to rewrite expressions to illustrate what we can do with some of the rules and properties of logarithms. So these are common logarithms. That means base 10. Remember, with base 10, you don't have to actually show the base, the subscript of 10. You can just write log, and it's understood that it's a base 10 logarithm. So we'd like to express log of 15 in terms of log of 3 and log of 5. And that's fairly straightforward because we know that 15 is 3 times 5. Then by the product rule for logarithms, we can split that up as log of 3 plus log of 5. So notice that the product turns into a sum. The logarithm of a product becomes a sum of logarithms. And that's as much as we're going to do. Just rewriting log of 15 as the sum of log 3 and log 5. That's an application of the product rule of logarithms. The second example, log of 125 over 3. Well, a couple of things to note. obviously there's a quotient involved, but also in the numerator, 125 is a power of 5. It's 5 to the third power. So let's write it that way. Log of 5 to the third over 3. Now this is just a single logarithm of a quotient. By the quotient rule, that can be split up as a difference. Log of 5 to the third minus log of 3. And then by the power rule for logarithms, the power that 5 is raised to, the exponent that 5 is raised to, can be moved to the front of the first logarithm. In other words, 3 times log of 5 minus log of 3. So again, we've expressed the logarithm of 125 over 3 as, or in terms of log of 3 and log of 5. 3 times the log of 5 minus the log of 3. And that's as far as we're going to go with it for now. Let's look now at example 2. Find the exact value of the logarithm using logarithm rules and properties. The first one, log base 3 of 1/3. I'm going to show you two ways that you can find the value of this logarithm without converting. Oh, actually, I'll show you 3 ways. How does that sound? Very exciting. Log base 3 of 1/3. One way would be, since we're just talking about it now, would be to use the quotient rule to write this as a difference of logarithms. Log base 3 of 1 minus log base 3 of 3. Then you have to remember some of the properties that we talked about in the previous section, and I need to write those somewhere, so let me just write them kind of down below here. One of them was that for any base a, the log base a of 1 is equal to 0, and also that the log base a of a is always equal to 1. So making use of those two properties, the first logarithm is 0, the second logarithm is 1, log base 3 of 3 is log base a of a with a equal to 3, and 0 minus 1 is negative 1. So the value of the logarithm is negative 1. Here's a second way we could do it. We could say that log base 3 of 1/3 is identical to log base 3 of 3 to the negative 1 power. And then we could also mention a third property of logarithms. Log base a of a to the x is equal to x for any base a. And if we have log base 3 of 3 to the negative 1, this is sometimes referred to as a cancellation property of logarithms. We can cancel, and we just get what's in the exponent, negative 1. So there's a second way we can obtain negative 1. A third way would be log base 3 of 1/3. Let's call that y. Convert that to exponential form. 3 to the y equals 1/3. Then solve for y. Y is the exponent 3 should be raised to give us 1/3. That exponent would have to be negative 1. So we found the exact value of log of 1/3, log base 3 of 1/3, using the quotient rule, using the cancellation or inverse property of logarithms, or by converting first to exponential form. All of these, of course, gave us the same result, just 3 different ways that we can approach the same problem. We'll continue with section 4.3 notes in the next video.